So this morning, we're happy to have Matthew McIlree here at the Meow seminar, and Matthew will tell us about proof logging for constraint programming solvers. Matthew, please, the floor is yours.
Thank you very much. So yes, I'm here to talk about my PhD research, which I've been working on the last 2 to 3 years with my supervisor, Kieran McIlree, and with collaboration with various people, including the University of Copenhagen, on certifying the output of CP solvers using the technique of proof logging. So just to explain some of the rationale behind this talk in particular, I'm kind of imagining here that I've got an audience that's at least a little bit familiar with certification and proof systems of some kind, but perhaps maybe less familiar with constraint programming specifically. So I'm going to try and make this a very zoomed out, very high level view of essentially everything that's been done in proof logging for constraint programming over the last, honestly, it goes back really 15 years if you go back to the earliest paper that I'm aware of. So it'll be a little bit of a literature review in talk form, and there might be time for technical discussion afterwards. So I'll get into it. So like I say, I'm assuming you're probably familiar with the idea of proof logging, but just in case not, this is a method to make the output of combinatorial solvers more trustworthy. So in normal terms, we have a problem description that we feed to a constraint programming solver, and this will produce an answer. And if you're using this from the outside, the process of the solver might look a little bit like a black box, and you may not trust the answer that comes out, especially because we know that constraint solvers are often very complex pieces of software that could be prone to bugs. So the grand solution of proof logging is that the solver should also produce a mathematical proof of correctness. And the philosophy here is that the proof should be produced line by line, effectively getting the solver to show it's working. And at the end of the process, we feed the problem description, proof, and answer into an independent proof-checking tool that's ideally a much simpler piece of software that we can trust in itself. So normally, I would go into the specifics of talking about what we've done in proof logging for CP, but instead of talking about the proof side of things, I'm going to first talk about the CP solving type of thing and get into the sort of constraint programming viewpoint. So constraint programming, as you're probably aware, is a declarative paradigm for solving hard problems. We view things in terms of variables, domains for those variables, so possible values they can take, and constraints. And in the most general view, all of these are just sets of symbols. So variables are just symbols, and domains are just some set associated with each symbol. And constraints, it's kind of difficult to define in the most abstract sense, but we can kind of settle on the idea that a constraint is a predicate that you can evaluate over these symbols when associated with values in their domain. Now, this is obviously far too abstract in general to apply. Most of the time, we need to take some kind of restriction of this definition to talk about combinatorial solvers that we actually care about. But what's quite nice from CP people is that we can view basically all other combinatorial solving paradigms as essentially special cases of constraint programming. So the well-known Boolean satisfiability paradigm is just a constraint programming problem where all the domains are 0, 1, true or false, and all the constraints are propositional clauses over those variables, a clause being evaluated to true if at least one variable in the clause is set to true. Of course, you can also have negations of variables. I probably should have put that in there. If you allow the domains to be non-finite, you can also view mixed integer programming as a kind of constraint programming as well. Although in practice, when we talk about CP as opposed to just the general constraint satisfaction domain, we're really talking more specifically about finite domain variables. And we normally assume that these are integer finite domains. And probably we also assume that these are ranges as well. So domains would look something like this: x in 1 to 5, y minus 3 to 7, etc. And we're pretty loose about what sort of constraints we'll allow compared to other paradigms. So we have linear, nonlinear, inequalities, not equals constraints. We might allow multiplication and more complicated arithmetic expressions. And we also allow more complicated global constraints that can operate over a non-fixed number of variables. So the classic example would be the all different constraint. So this just says that whatever number of variables you give to this predicate, they must all take different values. Constraint programming can also be viewed as an optimization paradigm by associating an objective function with one of the variables. So you're just saying you want to maximize that variable's value within the domain subject to the constraint. So it's a constraint satisfaction problem associated with an objective value we call a constraint optimization problem. In practice, we don't just allow whatever constraints you could ever think of, but we restrict to some kind of set of constraints that are recognized by some kind of constraint modeling toolkit. So there's several high-level CP modeling languages that allow you to express constraints and essentially declaratively express your problem using higher-level constructs like for loops and various other things. And this will then get compiled down to essentially a flat list of constraints that is of some recognized set. And you might have to decompose certain constraints depending on the underlying solver that you're using. So each solver will have a set of constraints that they support, and the higher level modeling language will be responsible for decomposing to that format. But basically, CP is good when you have various different kinds of high level constraints that interact in interesting ways. And a CP solver might be more suited than having to encode to a lower level format like SAT and solve on that level. So just a quick
Question.
summary of how, yes?
So you already, if you touched on this already when you talked about the difference between CP and MIP solving, but is it true in constraint programming that integers are always fixed bit size objects? Is this just a philosophical difference, or is there also constraint programming where you would think about like arbitrary precision integers, or this is just not a thing in CP?
So it depends what CP viewpoint. I think the problem is that constraint programming is sort of used to mean two different things. And Kieran, who's in the talk, can maybe back me up on this a little bit. But there is this super abstract high level viewpoint of constraint programming problems that is interesting from a theoretical perspective, which absolutely you can have non-finite integers and whatever constraints you like. In practice, it just depends what your particular solver supports. So these high-level CP modeling languages, they might compile your problem down to a MIP problem, in which case, yes, the CP solver, which is really a MIP solver here, can deal with arbitrary precision integers potentially, or whatever that solver might support. But that's kind of the first use of the word CP to talk about the modeling process. We then go on to overload the term CP to talk about what might be better termed finite domain propagation solvers or something like that. And in general, these do not support unbounded integers. They don't even support floating point integers for the most part, and they basically reason about bounded sets. Some CP solvers support set variables, so variables that are effectively sets of other variables. Others don't. It really depends on the particular solver. Does that answer that question?
Yeah, kind of, but maybe it's just a historic difference because my impression is that if you talk to based on my limited experience, but my experience is that if you talk to a CP person and you say that an integer is say a 64-bit object, then this CP person would agree. But if you talk to a MIP or a SMT person, then maybe actually maybe the MIP solver would, in fact, also treat integers as a 64-bit object, but somehow the MIP person will not be happy to think about it this way. It really wants to think about an integer as an integer, and addition shouldn't wrap around, whereas it seems like a CP person is like fine with this, that because of course, it's a 64-bit object. So, but maybe that's just historically how the fields have developed. I don't know.
Yeah. Well, certainly what I can say that for the certification stuff that I'm going to talk about, we absolutely need to assume that we can encode every integer with a maximum number of bits. But we'll maybe get to that part when we get to it. So coming first to the inference part of CP solvers, which is really the main reason you would want to use them. So essentially, these finite domain propagation solvers associate with every constraint some kind of inference algorithm that allows you to remove values from variables domain depending on that constraint. And if you remove the maximum number of values that would be theoretically possible to remove, we say that you've achieved domain consistency based on that single constraint. But you might also just trim the bounds on the variable. So just decrease the maximum and minimum values in the domain. And we would call that bounds consistency if you do that maximally as well. So just as an example of simple inference, which you can clearly understand just by looking at it, if we had CP variables x with domains 1 to 5 and y with domains 1 to 3, and we had a simple inequality like x less than y, we would consider it a propagation inference to remove these three values from the domain of x, because if x took any of those values, then none of the values of y would be supported. I think that's right. If I've made mistakes in this presentation, please do point them out. Sometimes CP solvers reason over larger numbers of variables and look at the domains in a kind of more holistic way. And they might then decide that a particular set of variable domains is simply incompatible with a single constraint. So for example, if we had some variables with domains that look like this, and we had an all different constraint, v, w, x, y, z, then a CP solver should actually be able to immediately infer contradiction here, which might not be as obvious as the first example, although if you do Sudoku a lot of the time, you probably very quickly notice that we have these variables w, x, y, z, which have only 3 values in total between them, but that is 4 variables, and this is, of course, just the pigeonhole principle. And the important point is that CP solvers can evaluate this kind of reasoning efficiently, so that when you encode these kind of reasoning and propagation algorithms, you can often get it to speed up when these high-level constraints actually matter for solving the problem. Of course, inference is almost always not enough to just solve a problem on its own. So CP solvers also implement various kinds of search algorithms. I'll talk mostly or focus mostly on CP solvers that do backtracking search. So essentially, if you're familiar with DPLL algorithm from SAT, this is the similar sort of idea. We make decisions and we do as much propagation as we can at each decision level. And if we reach a contradiction of a particular constraint, then we have to backtrack. And if we find a solution, we have the option to either conclude, great, this problem is satisfiable, or we can add what we would call a no good. So we add a new constraint to the model, essentially saying, okay, now this solution is not allowed, go find more. And if we were solving an optimization problem, we might add a bound and turn this into a branch and bound algorithm, basically saying, okay, we found this solution, it evaluated the objective function to this, so we now need to do better than this objective value. So that is the whirlwind tour of how CP solvers work.
And can I ask a question about that?
Yeah, absolutely.
Because again, coming from more of a SAT background, going back to this, you had a quick slide on consistency. So yeah, for a SAT solver, I guess this is easy because the clausal constraint is consistent as long as it's not, as long as it's not violated, and if there's only one literal left, then that literal propagates. But now for CP, there are like more notions of propagation and consistency. So, but the consistency notion is for a single constraint. Is that correct? Like if I just look at
it can be. So for most constraint propagation algorithms, the standard is enforcing consistency on the variables in the scope of that constraint with respect to that particular constraints. There are also historically algorithms that enforce consistency across groups of constraints as well. So generalized arc consistent algorithms will do that. So there's basically as many different combinations of different levels of consistency that you can enforce on the different subsets of constraints as you can possibly think of. But at least in the CP solvers that I've seen, it's mostly about enforcing either domain consistency or bounds consistency on a particular constraint, one at a time.
And for a single constraint, you mentioned domain consistency and bounds consistency. Is And again, so domain consistency is just looking long and hard at the constraint and saying, well, if this constraint over X, Y, Z is to be satisfied, then I can rule out all the following values for X, say. You just puncture maybe somewhere in the middle, whereas domain consistency is somehow only, bounds
Bounds
consistency
consistency.
is only removing upper and lower bound. Is this important to understand for us?
I mean, not for this talk. I mean, it's important for understanding CP. I didn't put the formal definitions here because, in particular, there are three different conflicting definitions of bounds consistency, and in CP literature, it's not always specified which one is meant for a particular propagation algorithm. But in the most loose terms, domain consistency is poking all possible holes in the domain, and bounds consistency is reducing the bounds as much as possible, even if you're potentially missing holes that you could poke. And obviously, for many constraints, bounds consistency is both theoretically and practically easier to enforce because you only have to look at the max and min values most of the time.
And then there's arc consistency. Where does that fit into this picture?
So arc consistency is, I mean, I've tried to stop using the term. I'm
Ah,
not using it in my thesis because it's a little bit historical, at least from my point of view, tied to a lot of research that was done into constraint networks, which are essentially constraint satisfaction problems where you're assuming all the constraints are binary constraints over two variables. So you can then define a constraint graph as being the graph of associations of variables and their constraints. But generalized arc consistency is the same thing as domain consistency.
okay.
So I just say domain consistency now because as soon as you generalize, you're talking about multi-graphs and not graphs anymore. And it just the whole idea of arcs is a lot less intuitive. And I find it easier to just think about values with supports rather than consistency of arcs.
Okay, thanks.
But that's terminology, and it's not particularly important for this talk, thankfully. The most important thing for this talk about CP solvers is that they don't currently produce proofs. So that ideal slide that I put forward earlier, where a CP solver should produce a mathematical proof of correctness, and this should be verified, and thus we have much more trust in the solver, and we have a proof for all time that says that the objective value is 3. This is currently just not done. And it's not unreasonable to expect that CP solvers should be able to do this. So in the domain of Boolean satisfiability, it's pretty much standard practice for solvers to produce proofs. And wrong answers in the SAT competition are, as far as I'm reliably told, a thing of the past, which is not something we can say for the mini-zinc challenge. I always do a different thing in every talk to try and drive home the point that CP solvers get the answer wrong sometimes, because outside of the CP world, sometimes people are a little bit surprised to hear that actually it's pretty routine for CP solvers to get the wrong answer. So I went through all the results of the last mini-zinc challenge, which is the yearly or one of the yearly competitions for CP solvers, and I sorted by solvers that got the wrong answer. Now, it's a little bit annoying to report on this because unfortunately this error status also includes when solvers just ran out of memory on a particular problem. But I've been reliably told, and thankfully I'm with the mini-zinc authors here, that at least some of these error instances are indeed solvers just reporting wrong answers with respect to the metric of what most other solvers got. So obviously there's no proof involved here, but these solvers are maybe reporting optimality on a problem where they're reporting the objective value to be 12, and every other solver found the objective value, the optimal objective value, I should say, was 14 or something like that. So this is something that's affecting, as far as I can tell, maybe 1 in every 100 runs, something like that. It varies per challenge per year, but certainly CP solvers do produce wrong answers. And so they certainly should produce proofs. And being exact algorithms, it's not unreasonable to expect that they maybe should produce proofs. So I'm not imagining that this is an audience that needs too much motivation for the idea of using proofs in combinatorial solving. I'll be giving a version of this talk next week at a seminar precisely for the purpose of certifying algorithms and the philosophy behind that. So I'm going to assume from now on that you're sold on the idea that CP solvers should produce proofs and work towards what research has been done in order to get them to do that. So probably useful for the background is to go through some of what's been done in proof logging for SAT solving, just very quickly. So proof logging has quite a long history in SAT solving. I think some of the earliest work in what you could call proof logging goes back to 2003, where it was shown that SAT solvers effectively can produce resolution proofs, certifying their results. So SAT solvers obviously deal with clauses, so it's very natural that the proof system would deal with deriving clauses from a causal description of the problem. And effectively, you can get SAT solvers to derive all their conflict clauses using resolution, and this will allow it to output a proof, albeit it's not so easy to implement because for resolution, you need to know exactly what clauses you're resolving in order to write that down. So a bit of a breakthrough came in 2008, where it was shown that proof logging for CDCL SAT solving can be done by outputting all clauses as RUP steps. So this is another proof rule, which I will give a brief explanation of if that's requested. Would we like a quick explanation of RUP? I know the present audience knows what RUP is, but perhaps
No,
the more
I think
general
we
audience.
should definitely explain the concept of RUP. Also because I mean, yes, definitely.
Yeah. So from the most basic perspective, the best thing about RUP, at least from SAT solving or from a SAT solver author's perspective, is you don't actually need to know how it works in order to use it for proof logging. So the developers of the RUP proof format were able to just say, look, whatever you derive, if you're running CDCL, just output your conflict clauses and we will take care of the verification part. This magical RUP proof rule is enough to certify that. And this is highly related to what RUP is and how CDCL SAT solvers work. So for a quick RUP explanation, essentially we have a formula F, which is a set of clauses, and we want to derive a clause from that formula. And the RUP proof rule says that you can derive that clause if taking the negation of the clause and adding it to the original formula, and then running unit propagation, which is the SAT solver's most basic inference technique, just setting any units, so any literals that have to be set, and continuing to do that until you reach a fixed point. For this to be RUP, it has to result in a contradiction. So RUP stands for reverse unit propagation, and if the verifier can efficiently run unit propagation, then this can be efficiently checked. And so this is very nice. It's not hard at all to see that this proof rule is sound, because if we've effectively shown by the dumbest possible reasoning procedure that F and not C is unsatisfiable, then we've said this formula, just considered as a formula, is always false, which is the same as saying the negation of that formula, so not F or C, is always true, which just of simple manipulation of the logical notation tells us that C is implied by F. This isn't the most formal proof of soundness, I know, but it maybe gives you some intuition. So what this means is that any solution to F is also going to be a solution to C. So we can add it to the formula without changing the satisfiability, which means...
And in CP language, sorry, you said that the magic of just negating the constraint and then propagating. If we want to explain this to a CP audience, you would say that you do add the negation and then do bounds consistency propagation. Is that it or no?
For CP audience, we would say for clauses, unit propagation is iterative domain consistency, right? Because the domain is just 0, 1. So bounds consistency and domain consistency are the same thing at that level, because there is only two possible values. But I think most CP audiences as well are quite happy with the idea of clausal propagation. You know, if you have a clause constraint in your CP solver, then this will be the propagation that you run for it, probably.
But the way you will generalize it in 5 minutes from now, that will be bounds consistency.
Yes, although I won't go into that in a huge amount of detail.
Okay.
Because maybe rightly or wrongly, I decided that details of very PB could be left out of this talk. But maybe if we go into a more technical session afterwards, that would be more necessary. So then the next kind of major step in proof logging for SAT was, of course, DRAT proofs, which we're not going to go into, how the RAT rule, which is the core rule, replacing RUP, essentially generalizing RUP in this proof format is. But essentially, this was able to say for modern SAT solvers, if you're doing something fancier, you're doing some fancy in-processing or pre-processing techniques, then just the way that RUP had you covered for basic CDCL, then RAT has you covered for anything fancier that you're doing. And so they have a list of the different techniques, and they're able to show that these will all be RAT. And once again, the very nice thing about this is that solver authors don't need to care about how RAT works or how it's sound or how it should be verified. They can just add print statements to their solver to say, output our conflict clauses and output anything that the SAT solver learns, and this is going to be taken care of by the DRAT proof system. So this is very nice. It made proof logging very easy to implement, or comparatively easy to implement. And as such, because of the extreme benefits of proof logging for certification and for trusting your solver, for unsat proofs or for unsat instances, SAT solvers produce proofs basically as standard. So like I said, I've been reliably informed that unlike the mini-zinc challenge, wrong answers in the SAT competition are apparently a thing of the past. And also there's at least a little bit of acceptance of SAT solvers as being mathematical theorem provers. So there's some exciting headlines that you can look up in even non-academic media about gigantic maths proofs establishing long unknown conjectures. And this is mostly the work of McIlree and Hoyle, running supercomputers, which effectively are running a SAT solver and producing a DRAT proof. And because this is a proof and it's checkable and you can trust the checker, and they have actually a formally verified checker, so super trustworthy, then at least some mathematicians are happy to say, no, this is really actually establishing this mathematical conjecture. Although obviously, as this headline shows, but is it really mathematics? There's still a little bit of skepticism around that. But certainly us in CP are looking at this with a lot of jealousy and thinking this would be very nice, because we like to argue sometimes that CP solvers are automated theorem provers, because they are, in a sense, if you consider the proof system to just be constraint propagation and the proof checker in some sense to be the solver, then yes, we are proving things. But obviously the bugs in the solver makes this kind of difficult to assert, especially for mathematicians who need a high degree of rigor. So what has been done? Obviously, we've wanted this for a while. And probably the best place to start with proof logging in CP is to talk about how we even express the facts that a CP solver learns. Because in SAT solving, it's pretty clear. We have a clausal description of the problem. So we derive clauses, and this makes a lot of sense. Now, for a long time in CP, there wasn't really any sort of conception of what explaining inferences meant in these sorts of terms, in the way that SAT solvers can derive clauses. But actually, there's and this comes out of not efforts for proof logging, but efforts for making solving faster, turning essentially the action of propagators into what they call explanations. So there's not a whole lot of agreement on exactly what the most standard terminology for this. I'm going to use the term atomic constraints, which appears in quite a lot of places, which basically an atomic constraint is a CP generalization of a propositional literal. So this is the general format of it. We just say variable operation value, where operation is only one of a very few restricted things. And this tells you about the variable's condition with respect to that value at a particular point in search or propagation regarding some domain for that variable. I'm going to include the empty clause or the trivially unsatisfiable constraint as an atomic constraint as well, just for convenience. So what the observation, and this has been made for quite a long time in CP, is that, here are some examples of atomic constraints, just in case it wasn't clear. Obviously, the negation of these, I'm going to write these with square brackets, but the negation of these is just the corresponding operation. So the negation of x being greater than or equal to 3 would just be x less than 3 the negation of y not equal to 2 would be y equal to 2. So the observation is that propagators and the action of CP propagators can effectively be written down as a large sequence of what they call propagation rules, which are effectively a conjunction of atomic constraints implies another atomic constraint. And although it seems like CP solvers have a lot more information than this because they've got these huge domains potentially with lots of holes poked in them, it's always possible to break this down into just sets of atomic constraints and write any propagation action essentially as this form. So what the reason on the left-hand side is supposed to be is this is supposed to be as small as you can, a set of atomic literals that if that was all that the propagator knew, then it would still be able to infer this fact, which is also encoded as an atomic literal. And this can also be the empty clause in the case where the propagation algorithm is deciding that this particular state of domains is unsatisfiable. So just for some simple examples, here's an idea of a propagator explanation. Y being greater than or equal to 3 implies that x is greater than or equal to 4. This might be a valid explanation for a x being greater than y constraint. Here's another one. I'm not sure which constraint might make use of this, but as you can see, we use multiple literals on x to describe the state of domain where x is less than 4, and we've also poked the value 2 as a hole in the domain, and y is greater than 1. If this is the state of play, then we can infer contradiction. So effectively, you can understand CP propagators as just a gigantic list of every single possible propagation rule written in this form. But for any particular instance of a propagator's execution, you can write down one propagator explanation explaining that inference. And there's maybe multiple possible explanations depending on how general you want to be. And this is part of the philosophy behind lazy clause generation solving, which is a particular kind of CP solving paradigm, where effectively you use a conflict-driven search mechanism similar to SAT solving, or in some cases actually using a SAT solver that deals with these explanations, because these explanations, just like I showed before, these are just clauses. So if you're allowed to negate these literals, then these implied things just can disappear, and effectively you can discuss whatever a propagator action was in terms of a bunch of clauses. So if you can post these propagator actions to effectively a SAT description of the problem and run this in real time, then you can potentially get large speedups. At least that's the philosophy behind that. But it was also observed, so the use of these explanations for solving is kind of a little bit tangential from our proof perspective, at least at this point. But it's been observed, and this goes back to 2010, that these explanations could form some kind of proof format for constraint programming. So I think this is the oldest proof logging for CP paper. At least it's the oldest one I've been able to come across. So this goes back maybe 15 years now to 2010. So this is the proof producing CSP solver. And basically what they said is we know from SAT solver research that backtracking search and conflict-driven search can be efficiently described with a resolution proof system. So a CP solver could also output unsat proofs if only we can trust these explanations. So effectively what they did is they set up a CP solver to output a resolution proof, but wherever the resolution proof would have relied on a clause that can only be inferred due to the propagation of a CP solver, they had a trusted proof rule integrated into their proof system that they effectively said, okay, we're now going to define a propagation rule in our proof system for, say, the all different constraint, or I think in their case, they used the no overlap constraint as an example. So here's what their sort of proofs would look like. So they used a not in instead of a conjunction of reason literals. So this is effectively a proof that says, okay, we'll introduce this constraint as a premise. So this is a CP constraint written in CP language. And now, due to this constraint, we can introduce this clause, and this is due to a special proof rule for this no overlap constraint, and so forth. And we can continue to do this. And then when it comes to the actual points in search where we're wanting to backtrack, we can effectively output a resolution proof that allows us to derive successively more and more general no goods, so more and more general clauses that are disallowing values from variables domain until we can eventually derive the empty clause. So this is a resolution proof, and it is effectively can be thought of a proof system as a proof system where we have specialized propagation rules for every constraint. Now, from a proof logging perspective, obviously this makes a start in that we now can think about what CP solver proofs even ought to look like in terms of, okay, we have effectively a resolution proof skeleton, and we're filling in these explanations, and we're relying on trusted proof rules. But it does slightly go against the philosophy a little bit of proof logging in that we want the verifier to be as simple as possible. So if we're going to augment our verifier with many, many proof rules for every single CP constraint, then we're effectively verging onto the danger that our verifier becomes as complex as our CP solver. Now, depending on what you want to certify and depending on how much you're willing to put in what's being termed as the trust base, this may or may not be good for you, but certainly for strong mathematical guarantees, having a verifier that supports all of these proof rules is potentially not the most trustworthy. But this is the first CP proof logging work, so certainly it's very valuable from that perspective. So the second CP proof logging work is one that I've never talked about before, because it was unpublished, and that is a little bit unfortunate. As far as I've been reliably informed by the authors of this, or by at least one of the authors of this, it effectively remained unpublished for mostly logistical reasons due to the lead author leaving academia. But it's worth talking about how this CP proof logging approach works. So first of all, this extended this Wechsler and Strickman approach to deal with optimality problems. So basically, you can proof log CP optimality if you first have a trusted checker for a solution, and then you derive an unsatisfiability proof from the axiom clause that we must do better than this solution somehow. So what they did, and they used a lazy clause generation solver as the basic scaffold for this, is they used the SAT proof as a skeleton, and then they allowed this proof to pull in explanations that were already justified using an external prover. Now, this is quite nice because you don't need to have a model of the problem. You just need to trust that all of the explanations are correct, and then you can use the SAT proof as the skeleton. And what they did is they set up a formally verified, basically theoretical mapping of a CP problem in terms of higher order logic. So I think they used Coq in this particular example, and they set up essentially inference checkers that I would give you one single explanation, and it would tell me yes or no whether this is a consequence of that particular constraint. And then they had an implicational proof system that derived from all of these explanations the unsatisfiability of the final result. So this is kind of interesting. And here's an example of what their proofs look like. They had the problem where if you start with all of your explanation clauses as axioms, there are, of course, far too many explanations in order to make this practical. So they had a special syntax for introducing explanations, which is effectively like, in a SAT proof logging terms, like delayed introduction of axioms. But yeah, so they had this proof trace, and effectively this looks similar to what the Wechsler and Strickman approach was as well. So there's a slight complication where you have to be careful with a proof logging system like this. So this does seem very nice. So first of all, it relies on us having trusted inference checkers for every constraint. So although that's not strictly part of the checker, it does need to be part of the overall trust base. And you really have to write that in a formally verified way, which of course opens up the difficulty of writing formally verified checkers for difficult high-level constraints. But we also need to be careful if we're using modern proof logging formats like DRATs or VeryPB, which I'll come on to talk about, where what you're preserving when you're deriving clauses in your proof from what's come before isn't necessarily implication, but simply that the clause that you're deriving does not change the satisfiability of the formula. So this is an example. I took a while to come up with this, but this is an example that I think illustrates this point, where you have to be careful if you're allowing delayed introduction of axioms in your proof system. So here's a very basic CP problem: x, y in 1 to 5, two constraints, y is less than x and y is equal to 3, and we're minimizing x. So it should be relatively clear immediately that the optimal value of this optimization problem is 4. Y is, yep, x is greater than y is 3, so x can be at most 4. But if I'm not careful and I allow a proof system where you can introduce effectively redundant facts, so that is facts that are not implied but don't change the satisfiability of the formula, then unless I'm checking this with respect to the original model and I have a full description of the model, then I can actually evilly break the Ginge et al. Proof logging system. So here's the example of how you would do this. So suppose I have a trusted solution checker, which is possibly formally verified. So x being less than 5, I can introduce in my proof by appealing to this trusted solution checker and witnessing that x is equal to 5 and y is equal to 3. This is fine. This is indeed a solution. Y is equal to 3, x is greater than y. So I can then introduce in my proof by assumption a constraint that says, okay, this is a solution, so now I must improve upon this. So that's fine. But then I can start to exploit the proof system, because at the moment there's only one clause in the proof verifier's database. It's just this single unit clause, x less than 5, which doesn't have any particular meaning from a DRAP perspective or from a very PB perspective. This is just a unit literal. It's just a 0-1 variable. So I can introduce basically whatever I like at this point by redundance, because there is only one clause in the proof system. So I now have x less than 5 and y greater than or equal to 4. Okay, nothing's particularly broken yet. But now I can go for my delayed introduction of an axiom. So I'm supposing that I have a formally verified inference checker for the constraint y is less than x, which, you know, in the grand scheme of constraints is definitely one that should be possible to write a formally verified inference checker for. And then I can introduce this explanation and appeal to this formally verified inference checker, saying that if y is greater than 4, then x must be greater than 5. And this is certainly true. But now I've got a problem, and the problem is that I can immediately derive contradiction. And that's because I effectively contradicted this explanation before I introduced it by appealing to the formally verified inference checker. So unless you have a proof system that takes account of the original model when you start and doesn't allow you to introduce redundant clauses unless you check against this original model, then you potentially have a problem. Now, to be fair to the Ginge et al. Approach, they technically avoid this problem by having first the proof verified as a DRUP proof rather than a DRAT proof. So they have a resolution effectively, well, it's RUP, but they have a RUP-based approach, which, as we said before, is implicational. And then they only use the DRAT proof at the very end for formally verified checking. But then this does put the translation process or the carrying over process from this RUP proof to this DRAT proof. You're assuming that no one's tampered with the proof in the meantime. And so they have to say, well, this is part of the trust base. And effectively, any proof logging system does have to have a trust base. You know, even the formally verified DRAT format, you know, has whatever theorem proving environments and the axioms of that theorem proving environment and those software tools in the trust base. So there is always going to be something in the trust base. So I guess the philosophical question from a proof logging perspective is, how much do you want to have in the trust base? And what I'm going to argue here and for the rest of this talk is that it's better to have a unified proof system where you can derive your explanations directly in the proof system rather than having to appeal to external inference checkers. And it's not at all clear at this point whether this should be possible. I mean, certainly the Wechsler and Strickman approach did not consider trying to derive their clauses in the clausal proof format using resolution. And there's good reasons for that. We know that the action of some CP propagators are strictly theoretically hard to write down in terms of resolution proofs. I mean, the pigeonhole principle for the all different constraint that I showed way back is one such example here, where we know that you have exponentially large resolution proofs. And this is a theoretical result going back decades at this point. So now I can finally talk about the research that I've been more directly involved with, which is pseudo-Boolean proof logging for constraint programming. So the skeleton of this approach is basically similar in that we're still deriving effectively clauses for the outline of our CP search algorithm. So anytime we backtrack, we output a reverse unit propagation clause that encodes the negation of the sequence of guesses that led us to have to backtrack at that point. But what we do is we say, well, we will pay the cost of encoding the CP problem as a 0-1 ILP. So as a pseudo-Boolean problem. And then that allows us to use the stronger proof systems associated with pseudo-Boolean reasoning to actually derive these explanations directly in the proof. And the main proof system that we use for this is cutting planes, although the very PB proof system, which is developed in conjunction with the University of Copenhagen, who are very kindly hosting this seminar, allows for a broader variety of proof rules, which unfortunately I'm not going to talk about in great detail because I'm trying to give a more general literature review here. But I am going to show, so there was this paper I should have said, which was the original paper on justifying the all different constraints, so showing that the explanations for all different can be derived using cutting planes. And then this was generalized into a proof framework for a general CP solver that deals with several global constraints, quite a number, essentially a bunch of the fundamental constraints that you would want to support in effectively any CP solver. So linear inequalities, the element constraints, I'm trying to remember off the top of my head, not equals, and table constraints. I think these were the ones that were covered in this paper, which is already a significant enough toolkit to run many CP problem benchmarks. So although I'm not going to go into the full specifics of the very PB proof system here, I will show a worked example. And we've already seen what general proof scaffolds, if you like, for CP problems look like. So I'll instead just show how we can justify just one explanation in CP proof format. So imagine we have a linear constraint, 2x plus 3y plus 4z is less than or equal to 42. The explanation for this constraint, if we propagated something due to, say, x being greater than 5 and z being greater than 3, and understood then that y is less than or equal to 6, would look something like this. And you can verify just by looking at the bounds here. If x is greater than or equal to 5, then the contribution of this first term is 10, and the contribution of this third term is 12. So we've got 22 overall here, which means we've only got 20 left to play with, which means that y certainly can't be 7, otherwise that would give a contribution of 21. So a CP solver should be able to infer this, and if we're working in some kind of RUP-like resolution-like proof framework, we need to be able to derive this explanation in the proof. So this is how we can do this with pseudo-Boolean reasoning. So first of all, the very PB proof format does allow us to introduce redundant clauses, as I mentioned before. Redundant constraints, because we're now talking about general pseudo-Boolean constraints that are not strictly just clauses. These are general 0-1 integer linear inequalities. So x being greater than or equal to 5 implies, and what we're going to do is we're going to encode the CP variable x as a bit string. So this is the exponential sum, essentially evaluating the bit values of this CP variable. If we were to encode it as a 4-bit integer, it's greater than or equal to 5. So we are viewing this in the pseudo-Boolean world as the canonical representation of this CP variable. And this atomic constraint is simply being reified on this CP variable. And this is, of course, a redundant constraint if we've never seen this literal before. If we have seen this literal before, then by assumption, we would hope that this had already been defined. So we can do the same thing for z greater than or equal to 3. Again, this is a redundant constraint. And I'm going to use the negation of the literal just to make a little bit clearer here. We can also derive the negation of y being less than or equal to 6 which would look like this. So the bits of y would then be greater than 7 because that is the negation of that. So again, these are all redundant. Essentially, this is an implementation of an extension rule from a proof complexity perspective. We're deriving new fresh variables reified on constraints. And then what we would assume is we would assume that we have already encoded our linear inequality in pseudo-Boolean terms as part of the input model for that proof system. So we're for that proof checker. So we're changing the viewpoint here a little bit in that instead of giving the CP's solver's model directly to the proof checker, we have to encode it first in a language that the proof checker understands. But certainly for linear constraints and for all of the constraints that were dealt with in the previous paper, this is very straightforward to do. So unlike SAT encodings, which can be very difficult to encode these kinds of linear inequalities, we can pretty much directly translate a linear constraint like this in CP terms into a pseudo-Boolean constraint by effectively squinting and just pretending that each of these finite variables is in fact that exponential bit sum. And then, of course, all we need to do is multiply up the coefficients so that this is a correct representation of that constraint. So what's very nice here is that we can now use the power of cutting planes, which was not a proof system that we had in our toolkit earlier. So if we take these three reified constraints, which if you're familiar with pseudo-Boolean solving or integer programming more generally, these can be written just simply with big M notation. So we just take the negation of the variable reifying the constraint and add it to the constraint we want to reify and negate it. So if this constraint was ever false, if this variable was ever false, then the constraint would be trivially satisfied. But if it was true, then this term disappears and we have to satisfy the constraint. So this is semantically just exactly the same thing as the reified PB constraint. But now cutting planes allows us to take linear combinations of things. So this is a fundamental part of the cutting planes proof system, is that you can add up and multiply by scalar coefficients. So like I said, I'm not going to go into the proof system in full detail here, but this is essentially what you can do. So this gives us, once all the dust settles and we cancel all the variables, if we multiply the first constraint here, this redundant constraint, by 2, and the second one by 3, and the third one by 4, and add everything up, then we get something that looks like this, which if you stare at it for a minute, you'll realize is just exactly the same thing for the same reason as what I said earlier for these top three constraints. This is exactly the same thing as the explanation that we wanted to derive. So that's a little bit of a quick example of how cutting planes can be used to justify integer linear inequalities. I put this example in instead of the all different constraints because I thought it would be a little bit easier to digest. If we want, we can go over the all different constraint in the session afterwards. So how much time do we have? Approaching,
Question.
yes?
Question.
Yeah.
So here, do you in practice use the like implications only in one direction, or would you introduce like two-way reifications?
So for this specific explanation, you only need the one direction, but probably as we're defining our full CP proof, which we want to define in terms of these variables, we need to define both directions to get the RUP to work out. And I'm not going to explain that in the full amount of detail because I would probably need a slide to show what the full RUP proof looks like. But essentially, it's the same as the two proof formats that I already showed, where you use the conjunction of these literals as the conflict clauses, if you like. So in order for them to be RUP, we need them to be fully reified on the bit representation, which we're assuming exists in the model, in the PB model of the problem. Okay, so I think I'm running short on time, although I did start a little bit late.
So I think, yeah, so I mean, we're in charge of the time, and I don't think it makes sense to rush you when you have such nice slides. Question is, I mean, I think we could just continue, Or if you want, we could also take a 5-minute break now and then continue, but maybe that will disrupt the flow. I don't know. I mean, as far as I'm
it's
concerned, you
worth
could just keep
saying.
going for as many more minutes as you like. I mean, that's fine.
So these next 5 dots up here are mostly just me flashing papers that have appeared since, and very briefly saying what happened. So I'm not going to go into any technical detail. The idea was to offer, if anyone wants a more technical explanation on the whiteboard of any of these constraints, I can do my best to try and explain what the PB encoding we used was and how we derived the justifications in PB terms, because this has basically been my PhD research up to this point. But we can take a break before that. I don't really mind.
Why don't you just continue at the leisurely pace, and then we'll just see where we end up. Okay? But
Sure.
there's no need to rush it. Okay, so keep going,
Sure.
please.
Cool. Okay, so yep, like I say, this is the point where I started doing work in this field. So I'm now shamelessly plugging research that I was personally involved with. But I do think at least between 2022 and 2024, these were the only papers that were coming out in proof logging for CP specifically, because now we have this idea, this foundational viewpoint that actually you can justify CP explanations using essentially cutting planes in this lower level PB proof format. Then the natural question arises, well, okay, this was fine for linear constraints, and this was fine for all different, and this was fine for the things that appeared in that original auditable constraint programming conference paper. But there are a lot of CP constraints out there. And is it the case that some of them might show up that are fundamentally hard for cutting planes somehow, or even if not hard on a theoretical level, at least annoying to implement in any sort of feasible way? So what I've been looking at over the course of my PhD is essentially different categories of CP constraints and trying to figure out how we can derive pseudo-Boolean justifications for the actions of the propagators. And in effect, ticking off as many constraints from any constraint catalog as I possibly can. So the first one that I ended up looking at is a generalization of a table constraint. So a table constraint you can just think of as enumerating all possible tuples of solutions for a particular constraint. So the table representation of the all different constraint, which is not one you would want to use, but you could, would just be all possible values that are all different written out as rows of a table. So 1, 2, 3, 4, 5, 6 would be the first row, and 2, 1, 3, 4, 5, 6 might be the next row, and so on and so forth. So you have a table constraint, and this can obviously, for some constraints, like all different, be exponentially large. The idea with the smart table constraint is essentially to compress this table representation, but rather than having values as the tuple values directly, you allow simple binary and unary constraints. So effectively, if you're more happy with SAT terminology, this is like a disjunctive normal form. So each of these rows in the table is saying the conjunction of these little sub-constraints must hold, and then the whole table constraint is saying at least one of these many constraint satisfaction problems that we've defined via these rows must hold. And it turns out this can be a really useful way, a compact way of both expressing and propagating a bunch of constraints. And what we kind of ended up showing more generally, although this wasn't
just
really
to
the focus.
double check, sorry, the understanding that the way to read this smart table constraint is that if I pick a row, and if I satisfy all the constraints in that row, or like all the conditions in that row, then I'm guaranteed that my constraint is happy. So for instance, like for the first row, z equals 3, y equals 2, and x equals 1, then since I satisfy all of these constraints, I know that my constraint will say, yep, this is a good assignment.
Precisely. So I'm telling you, I don't care which row you pick, but you better satisfy at least one of them. So it's like I said, that's why it's a bit like a disjunctive normal form, because it's like an or over all these rows, where each row is an and over these atomic, well, they're not atomic constraints, but
and
call
of
them
course, there's
smart
no reason to believe that in a smart table that the rows would be exclusive mutually. I mean, that's not necessarily
So
the case.
yeah, there's no reason that the rows have to be mutually exclusive. So you could satisfy multiple rows at once, which isn't normally the case with table constraints, because there's no reason to put in exactly repeated rows in a table constraint. But there might be multiple ways of expressing things in a smart table constraint such that you do satisfy multiple rows of the table. What is kind of interesting to observe here is that there's no reason particularly why you have to restrict the entries of these rows. So from a solving perspective, you want to restrict the entries because you want to concentrate on things you can propagate really fast and efficiently. From a proof logging perspective, there's one theoretical guarantee, which I won't go into right now, but providing that theoretical property is satisfied, basically any conjunction of disjunctions can be proof logged in the way that we describe in this paper, which is quite powerful because it is effectively us saying, if you know how to proof log these simple constraints, then you can also proof log any constraint that uses those constraints in a decomposition. So this is very nice and allows us to immediately cheekily tick off a gigantic number of constraints from the global constraint catalog, even if we've not added proof logging justification derivations directly to those propagators. We can at least be confident that we can process the proof in some way in order to expand any of those justifications out into a smart table justification. So this is one thing. Another somewhat similar, although the focus of this paper was slightly different, thing that we can guarantee to say is that if you can express the action of your solver in terms of a decision diagram algorithm, and that you can efficiently express this decision diagram inside the proof system, then you can also proof log that as well. So the example from this paper is knapsack constraints, which is something that you can actually integrate into a CP solver as a constraint. Also, in the previous paper, we talked about the regular language membership constraint, which tells you that a sequence of values must be a member of some regular language that you specify in terms of a deterministic finite automata. And it turns out this can also be efficiently propagated as a decision diagram effectively. So we have a proof logging procedure for arbitrary decision diagrams, which means any decision diagram or multi-valued decision diagram constraint can also be proof logged using pseudo-Boolean cutting planes type justifications. Also, in sort of work I've done, I've kind of zoned in on some more particular constraints, especially ones that people might look at and go, this is quite far away from pseudo-Boolean integer linear inequalities. Are you sure that you can do this using cutting planes? So the circuit constraint is in fact a graph constraint. So it's actually specified in terms of variables being equal to a value is like a successor representation. So if the variable x2 is equal to the value 3, then that's representing in some abstract sense that in a particular graph, there is a directed edge between the node 2 and the node 3. And then the circuit constraint is saying, interpreting the variables in this successor representation, we must form a Hamiltonian circuit. This is very important, very useful for using CP solvers to solve vehicle routing, traveling salesman type problems. And of course, it's NP hard to enforce full domain consistency on a constraint like this. This is not surprising to anyone that knows about Hamiltonian circuits. But there are ad hoc propagators that turn out to be very useful in practice, that basically it's not poking all the possible holes, it's just poking as many holes as you feel you can get away with. And what we did is we went through all of the propagation algorithms that we could find that were implemented in state-of-the-art CP solvers and showed that all of them can be boiled down to effectively a similar sort of counting argument as was used for the all different constraints and construct pseudo-Boolean justifications for this as well. So there's no barrier to doing it for circuit. There's no barrier to doing it for any constraints that we can decompose or express as an MDD. The final kind of paper that I've worked on that's worth talking about is proof logging for bounds consistent multiplication, which was just this year. I presented this. And this paper is kind of an interesting one because it's maybe the first one that starts to verge on demonstrating that pseudo-Boolean justifications have some limitations when it comes to CP. but it kind of depends on your point of view. Certainly the way we talked about this in the paper, we are showing that you can do efficient PB justifications for integer multiplication. So when I say bounds consistent multiplication, I mean looking at a nonlinear constraint x times y equals z and inferring based on the maximum and minimum values of two of these variables domain what the maximum and minimum value of the other variable has got to be. Now, even just expressing this constraint in a PB format is a little bit tricky because, somehow pseudoboolean is dealing fundamentally with linear constraints, and this is something fundamentally nonlinear. So again, I won't go into this in detail, but we have to express all the individual bit multiplications and then effectively build a multiplication using nested additions. But we can write down this constraint in a pseudoboolean form, and it does take n times m PB constraints, where n is the number of bits of x and m is the number of bits of y. But if we're willing to accept that cost, which may or may not be acceptable to you, depending on your use of your solver, we can construct pseudoboolean justifications for this as well. And we have some slightly awkward derivations because you have to case analysis on negative values, which mess up bounds consistency in all kinds of horrifying ways. But yeah, here's a quick summary of all the CP constraints that we know how to do pseudoboolean justifications for so far. So these ones are all implemented in the Glasgow constraint solver, and were mostly done before I started, mostly by my supervisor, Kieran McIlree, and his collaborators. And then these ones are ones that I more specifically worked on, including the categories of constraints that I talked about just now. If anyone wants citations or to be pointed in the direction of any of these papers, this last bullet point is unfortunately unpublished, but we're hoping to maybe integrate it into future work. There are still many, many more constraints, obviously. I use this scrolling credits slide in every presentation because it took me so long to render it in the first instance. But that's the entire global constraint catalog. It's still an open question technically whether some of these may have real problems for pseudoboolean justifications. We already got to a point with integer multiplication where it's doable but maybe not ideal. But certainly with the very large number of kind of categories of constraints that we've shown now must have efficient justifications without us actually implementing them. It's basically close to say that the vast majority of CP propagators that you would actually want to use and that would be supported in a solving toolkit like our modeling toolkits or like MiniZinc can be justified with pseudoboolean justifications, which means that in principle, we can do pseudoboolean proof logging for all CP solvers. Of course, the question then arises, right, if we've shown this and pseudoboolean proof logging is working so well for us, why isn't the CP community jumping on top of this, and why aren't all CP solvers producing proofs already? I mean, proof logging is such a great thing, and basically no one I've ever talked to has ever said that this is a bad thing to aspire to or something that they wouldn't want for their solver. But there's some challenges on top of knowing what solver and what propagation algorithms we can efficiently justify. The first one is, from what we've reported so far, there can be quite painful overheads on top of solving. Part of this is to do with just writing to disk. Part of this is to do with adding non-trivial computation to the propagation algorithm of our CP solver, which is, of course, the most sensitive area to add any kind of overhead to. But this is a graph, a kind of sad graph that we had in our proof logging for the circuit constraint paper that showed for certain kinds of traveling salesman problem instances, we ended up introducing a 20 times roughly overhead on top of solving without proof logging by turning on proof logging. Now, we still are able to demonstrate a roughly linear relationship with the size of the problem versus the amount of work done by the proof logging solver. So theoretically, we're not blowing up exponentially, but we are potentially introducing a small polynomial overhead in some cases, and certainly we're introducing very large constant factors. So some of this is engineering, and some of this is we need to think about maybe more about how we can take some of this work out of the propagation loop and justify inferences a little bit differently. The other thing is, of course, we've put a lot of work into adding pseudoboolean justifications to the Glasgow constraint solver. it's not really expected at the moment that every CP solver is going to learn how the pseudo-Boolean very PB proof system works and figure out all of the bookkeeping you need to do in order to keep track of what constraints you've already derived and so forth in order to implement all these justifications directly. There's also verification overhead to be concerned about. I think generally solver authors are less concerned about this. You know, if I'm developing a state-of-the-art high-performance CP solver, I'm a lot more worried that your proof logging is going to get in the way of me being able to solve my problem quickly than being able to verify the proof quickly. But if the verification process is so slow that my solver now times out in the mini-zinc competition or in perhaps a future certified track of the mini-zinc competition, then certainly this is going to be something that I care about. And this isn't just for CP. Obviously, this is a question for all proof logging, making sure that we verify efficiently. Obviously, I already talked about the trust-based payment that we have to make, which is that at the moment we have an untrusted, well, it is trusted, but it's an unverified PB encoding of the problem that we're treating as the ground truth. And the argument we make is that this PB encoding is so simple that a little bit like the unverified verifier, it's a much simpler process, so we can trust it in and of itself. But we might want to look into formally verified PB encodings in order to increase the trust in that part of the problem. Very quickly, I should definitely talk about the one significant proof logging paper that has appeared in the last 5 years, other than the stuff that we've directly worked on. And this is introduced by a group at the University of Delft University, I should say. And this is essentially dealing with this problem that I mentioned before of adding lots of non-trivial work to the propagation loop of your solver by effectively saying, okay, how much time can we save if we don't add these derivations, these justifications directly to the propagator, but instead just output the proof scaffold with the unjustified assertions and then trim the proof effectively as much as you can, and then only produce justifications which you actually need. So if the derivations, particularly for something like the multiplication constraint where you're paying a polynomial overhead to compute them, certainly if you can get away with deriving fewer of them, this is going to be very effective. So this is certainly an approach that we would want to incorporate as well, and it's probably going to be necessary to do something like this to get any other CP solver authors to include proof logging. I'll maybe skip the Epicure up stuff for now in case we want to discuss this after a break, and I'll just skip straight to the conclusion. So if nothing else, sorry, were you... Okay.
I was saying that you can say maybe there's a few seconds about the Epicure thingy.
Okay, so all this is to say is this has come off just a very recent research visit. So I'm currently calling in from Australia because I've been visiting the University of Monash, and this Epicure up paper is effectively defining a standardized interface for SAT solvers to interact with external propagation engines without really knowing what these propagation engines are. And now that this exists, the people that generate lazy clause generation solvers are getting very interested because obviously the whole philosophy here hinges on using CP solver explanations and getting them to interact with an underlying conflict-driven, essentially search process. And having this interface means that you can use state-of-the-art SAT solvers. And all I wanted to say about this, and we can discuss this more, is that if SAT solvers are able to produce proofs in a variety of formats, including very PB, and CP solvers have these explanations that are being posted, and we know how to justify them in the very PB proof format, then it's definitely the case, I think, that we should think about an extension of this Epicure up format that also passes proof information between the external CP solver and the underlying SAT solver, because the SAT solver has the scaffold proof, and it also knows which clauses are needed at that point for a lazy clause generation solver. So it just makes sense that you would get the SAT solver to output the search part of the proof, but then you need to figure out how to get these CP solver explanations into that proof. And having personally fiddled about with the Epicure up interface for the SAT solver Cadical for the last 6 weeks, this is definitely not something that's supported yet. They do kind of mention in this paper that proof information is something they want to think about, but it's definitely not covered at this point. And it's hopefully going to get the opportunity to talk to some of the authors of this paper next week when they'll be present at Digital. So we'll see if any interesting research discussion comes out of that. That's all I really wanted to say about that point. So just quickly, I know I'm, yes, over time, very sorry. Just the conclusions, if you take away nothing else from this talk, proof logging is worth doing, generally speaking, and constraint programming solvers have a huge potential to be turned into certifying algorithms, even if they are not currently certifying algorithms and in the current state of the art. There's really no strong reason why they couldn't be or shouldn't be. This is a problem that is eminently solvable and thus a strong target for research. Pseudoboolean proof logging seems to be effective for a wide range of propagation algorithms. Basically, any propagation algorithm we have yet looked at, we've been able to find reasonably efficient pseudoboolean justifications for. But more generally, we do need a robust and usable logging framework that's easy for solver authors to use. So going back to the DRAP proof format, we're a long way at the moment for being able to say to solver authors, you don't need to care about how these derivations work, just output what your CP solver learns, and we'll be able to justify this and verify this. At the moment, there's quite a long way to go on that front before all CP solvers will be implementing proofs, and we can have a certified track in the mini-zinc challenge, and the world will be better. I put these open questions here, which I've already mentioned in the talk, but I thought if I was going to end the talk on a slide, I'll end it with the open questions. So thank you very much for having me, and I guess we'll be taking a break and then maybe having more discussion.
Thanks a lot, Matthew. Before you won't get off the hook that easily. I mean, we should also give opportunities to ask questions.
Oh, yeah. Questions now, of course.
And so one thing you mentioned already is the difficulty of writing the proofs. So my personal impression, rightly or wrongly, is that the reason proof logging is so successful in SAT is, as you mentioned during the talk, you really don't have to understand anything to write a proof. You're just saying, well, this is not quite true. If you really care about performance, then we know that maybe you should use the LRAT proof system, and that will be a little bit more complicated. But if you just want to have decent performance proof logging, the magic of the RAP rule is that you just say, oh, my CDCL SAT solver learned this clause. Please check that this is okay, and then you move on. So you can do proof logging without really doing anything. Now, as we've learned in CP, nobody seems to know how to do that yet. I mean, your papers in particular are getting more and more complicated. And you can also ask, as a constraint programming solver author, maybe I think that constraint programming is complicated enough, and I don't want to have to learn proof complexity and study papers on cutting planes. Do you think it would be possible to build some kind of tool chain for writing CP proofs without having to understand what the proofs are? And what would such a tool or a library or format or whatever look like?
So yeah, I think exactly that this will be the way to go. And it's something like the multi-stage proof logging approach. In some sense, like what was introduced by Delft, is going to be what we will need. Even there's the difficulty of it in terms of just knowing about proof logging and knowing enough about it in order to write the correct print statements into your CP solver. But then there's also the performance considerations as well as doing that. And I think a lot of CP solver authors would rather see the untrusted answer and then have to wait a bit longer for the proof to finish building, providing they've already got the answer as quickly as possible, than have to wait much longer for their solver to finish solving because it's also printing out a bunch of proof statements. So I think what we would need is, at least for pseudoboolean justifications, is a general purpose, what I've been calling a proof justifier. Unfortunately, the word elaborator is already overloaded in pseudoboolean proof logging. So I'm going to say justifier for a program that takes a trimmed proof with a bunch of asserted explanations and then expands out each of the assertions. Now, just looking at a causal explanation is not enough for PB proof logging or for an algorithm like this to know how to derive that explanation, right? Because the only reason any of this works is because we know what properties of different constraints to rely on. But if we were able to include enough hints in the proof format that we could expand this into larger pseudoboolean justifications, then I think this will be a strong way to go. And this is certainly something we're thinking about.
Do you want to say anything about the performance hit? Like what is it? I mean the size of the encoding, the generation of the proofs, the checking of the proofs, all of the above.
Yes, this is highly variable, and also we're asked for this all the time, particularly by reviewers and papers, and I don't always think that the raw numbers give the best representation of what the practical performance of proof logging in CP would be, because and a lot of the time we have not focused on making proof logging efficient. So with all of those caveats, the fact you're writing to disk, the fact that we're not streamlining the proofs, the fact we're not trimming the proofs, that being said, I think for the easier constraints, we're looking at maybe a factor of 2 overheads, sometimes a little bit less than a factor of 2 based on not running proof logging. And then, like you see, for some worse constraints like circuit, you could be looking at a 10 to 20 times overhead, which can be particularly nasty. Producing the encoding, on the other hand, is never particularly big because we're using to the full power of the expressiveness of PB constraints in order to get compact encodings for most constraints. Although, like I said, for integer multiplication, we do sometimes have to pay a polynomial overhead. But a lot of CP constraints can be encoded, especially the linear ones, as PB constraints in effectively constant time. So it's very quick to process the problem and produce the pseudoboolean encoding.
More questions from the audience?
Yes. So of this very long list that you showed, like on the slide behind it, there are about maybe 20 items or so that you know how to do, and then there, I think in the list there are probably over 200 or so. But how many of them are like special cases of something that you know how to do, or it's like, yeah, it's essentially the same technique as something you have done. Like how far have you progressed? Is it like 10% or is it more like 50%?
I confess that this is work I should do and that I have promised I will do for my thesis, which is to produce the pie chart, right, of this global constraint catalog. It's a little bit of a tedious effort because obviously each of these constraints has definitions and a lot of them were designed for very specific problem instances and they're all related to each other in different ways. I have not yet gone through them all and determined how many are special cases of stuff that we've already done. All I have done is looked at for particularly for smart table, just how many constraints can be encoded in that way. And I'm immediately finding there are many, many constraints that can be efficiently represented this way. So I'm sure when I go through this, we'll find that we are quite a significant chunk of the way through, but I would be just making up a number to say we know how to do 70% or something. I don't know. I know there are some constraints that we've specifically not focused on yet, in particular cumulative scheduling type constraints, and bin packing type constraints, difference logic. Some of these might turn out to be to come under some of the things we've done already, but I've not thought about it in particular. For cumulative, I tried some of the decompositions and didn't get very far, but I didn't put a huge amount of thought into it. So these are ones that are still open questions. So there are still ones that are genuinely open questions, and cumulative in particular is like a core mini-zinc constraint and is used in a lot of benchmarks. So it's not like some of these super esoteric ones that like showed up in one problem once in 1993 and never again.
Okay, so then I think we'll thank Matthew again, and we're taking a break. So we are back after the break, switching over to the second half, which, true to tradition, will be much more improvised, unstructured. Although it seems Matthew might be starting with some slides, so it's over to you, Matthew, again.
Great. Yes. So by popular request, I'm going to now go through some of the work that I've just talked about in a little bit more detail, specifically on constraint propagation, justification, derivations in the very PB proof format. And I have dug up some slides that I gave in a talk previously for a slightly more technical audience. So these slides are going to assume a little bit more knowledge of the very PB proof system, although I'll try and explain some things as we're going along. So I already talked about what the smart table constraint is, and hopefully we reinforce the idea. This is a disjunctive normal form over simple constraints, and the idea is that we can express a bunch of constraints compactly in this smart table form. So with the very PB proof logging methodology, we kind of need to, anytime we encounter a new constraint, we need to understand two things. We need to understand if there's a straightforward, trustworthy way of encoding this constraint in PB format. And then from that encoding, we need to understand how we can derive explanations, justifications in the desired form. So with the smart table constraint, I'm going to show you how we can prove some justifications at the top of search, imagining that we set the domains in a particular way and we made some propagation derivation. So first of all, I'll talk about how we encode the smart table constraint. And we make heavy use of the PB reification that I mentioned briefly in the first half. So essentially what we can start by doing is encoding each of these fundamental constraints in the smart table using PB constraints. And we do this by double reifying on a special selector variable, which essentially represents whether or not this entry constraint is satisfied. So for example, here, x being less than y, we can introduce, sorry, we don't introduce it in the proof, we actually define it in the model. So this is part of the definition of the smart table constraint here. The entry x is less than y if and only if, as you can see, the bits of x are greater than the bits of y. And we're normalizing this in PB form to be greater than or equal to 1. So this is pretty clear that this is exactly this constraint. And of course, this double reification syntax, as I mentioned before, is just a syntactic sugar for putting these constraints in this way. And we can continue to do this. So for y in the set 1, 2, we can define this. Since I have more time, I actually skipped this in the original talk, but I might as well write out this because it's not hard to write. So yeah, I should maybe clarify. Oh, that's a horrible eraser. I should maybe clarify. Can you see? Actually, if I'm switching between the slides and the whiteboard, I'll maybe stop sharing and then start sharing again. Does that make sense to do?
I think so, yeah. The whiteboard will be hard to see otherwise.
Yeah. Okay. So
yes, at least I do.
yeah. Okay. So in this original talk, I very suggestively put these dots and went, well, of course we can encode all of these constraints without having to go through each encoding every one. As you can see by the demonstration, it's a little bit fiddlier when you actually dig into the weeds of this, but really there's nothing untoward going on here. It's still very much under the umbrella of you can look at these PB encodings and maybe you confuse yourself only once, but you can agree absolutely these are these constraints with respect to the original bit variables, which is kind of the important thing when you're defining a PB model for a CP problem. So I've gone through all of the 6 entries in this smart table here. And of course, the philosophy behind using a smart table is that we're assuming that this is a more compact representation. So we're assuming that we don't have to define exponentially many entries. Otherwise, why would we be using a smart table in the first place? And then this allows us to define conjunctions as the actual tuple entries. So this is a selector variable S1 if and only if the three literals that we've decided encode the entry constraints are greater than or equal to 3. S2 if and only if the three literals that we've decided encode the entry constraints of the second row are greater than or equal to 3. And then finally, the encoding of the smart table with all of these literals defined is just at least one of these rows must hold. So that
And I
is
guess if you're not
encoding.
used to this, I mean, just to say that conjunction is just summing up saying that all the literals are true, which is your next last two lines.
Yeah.
And then disjunction is just summing up and saying that at least one is true.
Yeah. So
which is like a very convenient thing of pseudo-Boolean constraints.
Yeah. Pseudo-Boolean constraints can say at least one, they can say at least two, and a conjunction is just at least n, where n is the number of literals that you're dealing with. Or you can maybe think of it as just at least all of them, because it's an and. So this is smart table encoding. We're imagining that our proof logging CP solver output this encoding ahead of time, so at the start of the solving process. And now, so we're going to regard this as the input format for our proof verifier. And now we get to work on the actual proof. So this takes a little bit of the specifics of how the smart table constraint works, although it actually doesn't matter too much really about the efficiency of this. So like I said, there's this theoretical property that when you, and I remember how long it took me to make this animation, but when you decompose the tuple rows, so if you treat each of them as their own sub-constraint satisfaction problem, and you view them as graphs where the variables are the nodes and the constraints, and there's edges between variables if they share a constraint in common, then these graphs, for the smart table constraint to be efficient to propagate, that is, propagation on the smart table encoding gives you the same thing as propagation on the constraint that the smart table constraint encodes. That's a bit of a mouthful to say. But essentially, we need to ensure that these little graphs are acyclic. That's the theoretical condition that I mentioned earlier. And that's basically just saying this is a strong decomposition, if you want to think about it that way. So with that proviso, because we have a strong decomposition, then effectively what's been shown in literature on smart table solving is that propagating these individual constraints, so enforcing consistency on each of them in turn, and moving over a two-pass over these individual trees allows you to enforce domain consistency on the whole constraint satisfaction problem that is encoded by that row. Now, what that means is you can collect all of the supported and unsupported values for each row, and then it's pretty easy, just like it is for the table constraints, to identify values that have no support in any row, which is the same as a value that is incompatible with the constraint as a whole, and thus you can prune it and you can remove it by propagation. Now, what maybe is not emphasized in the original paper on this, but is something that we've kind of since come to realize and are maybe hoping to exploit a little bit more in future, is that even if your propagation algorithm did not use this two-pass process over a smart table representation to derive the inference, it might have gone away and done something completely different. We can still use that process as the outline for our pseudo-Boolean justifications. And we know if we're satisfying this theoretical property of the tree decomposition being acyclic, that we still get a non-blowing up. That's a terrible way of expressing this. We still get a compact number of proof steps in order to express this derivation, which is what we want. So there might be a more compact way of deriving the propagation inference for a particular constraint if you're not propagating it using a smart table and you use some specialized derivation algorithm. But this shows it effectively puts an upper bound on how long the pseudo-Boolean derivation can be, and also gives us a more sort of generic justification procedure that works on multiple constraints. So this is how this works. Effectively, all that we say is we're going to proof log this as if it is its own constraint satisfaction problem, but we're going to make everything conditional on the tuple selector. So S1 implies y is not 1. So this follows from this individual x less than y constraint, which it just happens to be RUP because this is a very simple PB constraint. We kind of skated over the proof of why these simple constraints are RUP in every place, which is why I'm now committed to actually writing down these RUP proofs in my thesis. But if you're willing to take it on my honor that simple comparison constraints like this do always follow by RUP, then we can derive by RUP S1 implies y is not 1 because if y was 1, then x would be less than that. And we're assuming, sorry, I probably wrote somewhere earlier in these slides that all of these variables have domains 1, 2, 3, in case that wasn't implicit. So yeah, this is a valid inference. We continue to prune values based on the domains of these individual constraints. So S1 implies y is not 3. S1 implies x is equal to 1 now because we've removed 3 from the domain of y. So y can only be 1 or 2. And since x is less than that, then the only value left for x is 1. So we can derive that. And then pruning this other subtree over here, there's only one inference to make from a z equals 3 constraint, and that is just the literal z equals 3. Now, what I'm omitting in this PB proof on the right-hand side is all the bookkeeping steps to derive these literals in the proof by redundance if they weren't defined already, which is something we have to do. But again, this is only however many literals you have. You only really need to do this once per time you use it because you can just refer back to earlier definitions. And unit propagation in the verifier kind of takes care of this for you anyway. So then we do the same thing for the other tuple. Again, we're treating this as a separate CSP. We're collecting tuples of allowed values and we're logging in the proof everything that we would log if we were solving this as a regular CSP, but conditional on the tuple selector. And so what we get is this bunch of inferences that are all RUP in this case. And in fact, for all of the basic simple constraints that are actually used in the smart table constraint, we managed to convince ourselves that these would always be RUP. Although if you allow views on variables, as some of the people here will know, unit propagation starts to fail you, and you might actually need to introduce some shortcutting planes proofs in order to derive these inferences. But the point is these are already constraints. We know these are very simple constraints we know how to justify. So once we have all these inferences logged, the overall propagation algorithm can keep track of the smart table feasibility and say, okay, is there anything here that is unsupported in both tuples? And in this case, y cannot be 1 either in the first tuple or the second tuple. So looking at the smart table constraint as a whole, we can say, well, y is just not 1. This is now an inference that follows from that constraint. So we can now justify this because we've logged all of these things. It's guaranteed that y not equal 1 will now follow by RUP. And that's because from these two constraints, this will unit propagate the two values of the tuple selector being false, which then contradicts this constraint in the smart table encoding. So that is how proof logging for smart table works. When we wrote this paper, I didn't really realize that we were relying on this property of proofs under implications, which has since been written down with a full case-by-case analysis of all the very PB rules in excruciating detail. That basically says, if we have a PB formula and a partial assignment, and that we can derive a constraint from basically restricting that formula under this partial assignment, then we can construct a derivation without losing basically any of the length of the formula, the length of the derivation of the constraint. The set of literals that were in the restriction implies that constraint that we derived from the restricted version. So this is the more formal way of saying, because we could prove all of these little subconstraints by basically pretending this S wasn't there, then we can actually prove it, that we can actually prove them subject to the assumption of S, basically. This is proof under implications or proof under restrictions. And it's like, if you work with pseudo-Boolean proofs, this is almost obvious. Like, it's one of these things that we've said, this morally just has to be true. But it was a little while before we actually got our head down and sat down and went through every very PB cutting planes rule and showed that if you basically just run the same derivation then the implications just kind of fall out at the end, subject to a little bit of patching up. So that's the material I had in the smart table constraint. We'll maybe take stock here of how people's appetite for more constraints is, or if there's any questions about this in particular.
I personally would be happy to take one more. I also want to go. I promised to say stupid stuff, right? You heard me before, so I'm happy to report that I succeeded, because what I said before regarding this GEC or LEC variables was wrong, and we don't want to go down this rabbit hole maybe, but just for the record to correct. What happens, what I said is true, is that if you just define why the implication saying that this equality variable implies that the sum of, I don't remember, what was it, z? If you have the equality variable implies z greater equal blah, and the same equality variable implies z less equal blah, that works fine. And propagation also works fine in the sense that if I'm not equal to 3, then the negation will propagate. But I think what Wietse pointed out correctly, and I was wrong, was that, well, suppose that you also want to have the propagation that the bit string actually says that z is equal to 3 now. And in this case, you want the equality variable to propagate to true. If you want that propagation, then I think you will need to write down, actually, you'll need to define a GEC variable that says this is what it means that z is greater or equal to 3. You define a separate LEC variable that says this is what it means that z is less equal to 3. And then you define the equality variable to say, oh, equality means exactly that both of these holds. And if you do this slightly more careful definition, then you will have full propagation in both directions, so that when the bit string is not equal to 3, then you propagate that the equality variable is false. If the bit string actually does evaluate to exactly 3, then you will have the propagation that the equality variable is true. Just saying this for the record, so because I claimed something different before.
Maybe the kind of broader point here is we're kind of touching a little bit on the philosophical distinction between the encodings and the proofs in terms of what information should be in the proof and what information should be in the encoding. Because when we wrote this paper, our encoding is effectively a little bit over-constrained. And actually, someone pointed this out at the conference. It's like, just to purely get a correct encoding of the smart table constraint, you don't need a lot of the reverse implications. But we have them there because it allows our proof logging procedure to just be a bunch of RUP steps rather than a bunch of cutting plane steps followed by RUP steps. It's at one level a little bit aesthetic, but perhaps from a philosophical perspective, really there should be less information in the encoding and more in the proof. And this isn't the only place where we've come across this. So another example, if I may use the board again, is in definitions of variables. Actually, I've got so much board, I'll just move my laptop. So when we're defining variables, if you define y greater than 3, if and only if bits of y are greater than 3, and y is greater than 5, if and only if bits of y are greater than or equal to 5, then really we need for proof logging in CP to just rely on the verifier to be able to take care of facts like, if I log somewhere blah 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 implies y is greater than or equal to 5, then I need to rely on y greater than or equal to 3 propagating in order for my RUP proof to actually work. Now, this will not necessarily follow, I think, from just the raw bits encoding, but we fix this by introducing also something that looks a little bit like the order encoding in CP terms, which would be y greater than 5 implies y is greater than 3. Now, this was going in the model, but it's really not hard to introduce this as well in the proof by RUP, because although just the very fact that there is y greater than 5 doesn't propagate this bit encoding to this bit encoding to y greater than 3, these two literals set these bit variables in contradictory ways, and you get this lovely ping-pong propagation that then gives you what you want. So this is rough. And so it's a question of, well, since we morally can introduce this in the proof, we probably should, and we probably shouldn't put it in the encoding. And so in the CP solver, we've actually removed some of the things like this and put them in the proof rather than the encoding, because we can derive them in the proof. And the whole point of this is the encoding should be as small as possible because it's our trust base from the CP perspective. I don't know if that made sense. Right. Well, I may as well talk about circuit because this is sufficiently different from smart table. So yeah, quick recap. I did explain this in the original talk, but quick recap.
We're now getting your view with seemingly the slide and the next slide.
On the next slide. Oh no, you're seeing my secret preparation.
Exactly. And I figured you didn't want to reveal that, leak that much information.
Spoil it. You see this now?
Yes.
No spoil? Okay, so coming back to our next constraint and final one of this more technical discussion, the circuit constraint, like I said in the original talk, is a graph constraint. We'll say it's on n variables, and we imagine every variable has the domain 0 to n minus 1. So they can all effectively encode the index of any other variable in this set. So I'll talk concretely about variables 0 up to 5, so 6 variables and 6 values. And what the circuit constraint encodes is if a variable x2 equals 5, then we're imagining that there's an edge between the vertices 2 and 5 in this directed graph, which doesn't actually exist in the CP model. It's just encoded by the values of these variables. So what the circuit constraint then says is together, these variables must take values such that when you look at the values in this way, it encodes a graph that is a Hamiltonian circuit. And this can be very useful, like I said, for encoding vehicle routing and traveling salesman type problems. So as I mentioned before, circuit can be propagated with an all different constraint because obviously the values have to be all different. But this still does not disallow situations like this where you have subcycles, which are not allowed by Hamiltonian circuits because you have to visit every variable. So effectively enforcing circuit, we already know how to propagate and proof log all different. So effectively the problem here is propagating and proving this no subcycle constraint, which is the NP hard part incidentally as well. So enforcing full domain consistency is NP hard, like I mentioned, but there exists many ad hoc propagators that do various things, and I'll talk about how we can proof log at least one of these ad hoc propagators, which is very, very simple, really. It's essentially just a one-step of look-ahead propagator, but turns out to be useful enough that this is actually used in various CP solver backends. So what I'm going to do to define a PB encoding for this is I'm going to introduce a binary encoded effectively CP variable P that doesn't actually exist in the CP model. So we ended up having a whole new way of bookkeeping this because this was the first sort of place where we needed something like this other than maybe table constraints with the tuple selector. But effectively, this is a proof-only variable. But from the proof's perspective, it is treated the same as CP variables. So it's encoded with a binary bit string, and you can introduce literals on it in the same thing. And the intended purpose of this variable is that the value of the variable pi will encode the position of vertex I relative to 0 in the Hamiltonian circuit. So looking over here, P0 by definition is obviously 0. P5 would be 1 because it's the first thing we visit. P1 would be 2 because it's the second thing we visit, and so on and so forth. So this kind of, some people call it distance metric. This kind of thing is well known in integer linear programming definitions of traveling salesman type problems. we can use a very simple encoding to actually enforce the no subcycle restriction, again with reified constraints by saying, if the CP variable xi equals j, then pj has to be exactly one more than pi. And we introduce this for every pair of values I and j. So for every variable xi and every j in the domain of xi. We need to do something different when we're reaching back to 0, and obviously we need to define p0 equals 0 and arbitrarily start somewhere. But this actually turns out to be enough to enforce the Hamiltonian circuit. And if you set all of the variables in a final solution, all of the p variables can only be set in a consistent way if you indeed have a full Hamiltonian circuit. And if you have a subcycle, they will contradict each other, because if you follow around a subcycle, if I went p0 equals 0, p5 equals 1, p1 equals 2, then p3 would have to, no, p0 would then have to be 3, but we already knew it was 0. So we're only allowed to circle back once we've seen everything, which is basically what that encoding is defining. So again, this is a pretty standard encoding. It's maybe a philosophical question, again, whether you consider this simple enough that we can just trust it. But maybe from a higher level viewpoint, this is something that is in our trust base, and it's simple enough that it's fair to say that it's in our trust base based on all the relative to all the kind of crazy propagation rules that the circuit propagator has. So I'll just do one propagation rule, which is the most fundamental for any circuit constraint, which is to do one step of look ahead and say, if I assign this variable, then I would complete a small cycle. And I'm not going to allow myself to do that. So imagining these thick blue lines represent variables that are actually assigned, as opposed to the thin gray lines, which represent variables that just have those values still in their domain. We have x2 equal 3 and x3 equals 4. So the circuit propagator should be able to do look ahead here and infer, well, x4 better not be 2, because then we've completed a small cycle. So how we can justify this in the proof log is basically, it's probably even simpler than the smart table encoding proofs that I showed you before. We can just add up these definition constraints. So we have from the encoding x2 equals 3 implies p3 is equal to p2 plus 1. We have x3 equal 4 implies p4 is equal to p3 plus 1. And we have x4 equal 2 means that p2 is equal to p4 plus 1. And if we add all of these things up, then we can see, just using cutting planes, that all of these p variables are going to cancel each other out. And they're going to cancel each other out precisely because this is a small cycle. So we've just basically derived the fact that that these three literals imply 0 is equal to 3 as a PB constraint, which is the same as just saying at least one of these variables must be false, which actually works as an explanation for any two of these things implies the other one, which is exactly what circuit propagators do. They just look at the assigned variables and say, well, you can't assign the head variable to the tail variable. So effectively, the propagators work on efficient means of actually recognizing these chains of variables and keeping track of how many chains we've made. And if we contribute to a new chain, we need to make sure that we prune all the related values. But actually, proof logging does not need to worry about any of those efficiency things. It just needs to know, well, we're always proof logging this principle that we're removing the domain of the start of the chain, or we're removing the value of the start of the chain from the domain of the end of the chain. And this will always work. So that's an explanation for a basic circuit propagator. And in fact, there are some CP solvers where this is the only thing that is implemented for circuit, and that's enough. There is more, and I do not have worked examples for it. There is the CPIOR paper where we go into this in excruciating detail, and still not enough detail. I'll need to go into it in yet more detail in my thesis, because some of the other propagation rules for circuit are a little bit annoying, but partly what has spawned those large overheads that I showed in the other place. But at least for this is very nice, and this is very neat, and again shows a very neat cutting planes argument to justify a combinatorial CP propagation inference. So
and what you're telling us, And what you're telling us that if we're complaining that you only did a small toy example here, then we should go read the CPAIOR paper where you essentially build cutting planes proof for what? For almost everything that is on the Hamiltonian circuit market.
Yeah, it's a little bit tricky to say. So first of all, although this is a toy example in that it is small, like the principle of this is entirely encapsulated on what I put here. And this is enough to propagate circuit in a large majority of cases. Or I've not reviewed every CP solver and seen what they implement for circuit, but not every CP solver implements the strongly connected components propagator, which is the bigger, more awkward thing. But yeah, the CPIOR, I mean, I think I had more slides on this. So I talked about what that propagator does, and just on the very highest level, what we do in the proof. Effectively, we're running a transitive closure argument, I think is what we decided. It's a counting argument similar to what we do in all different, where we effectively derive successfully bigger sets of these PB variables being equal, these P variables being equal to some value until we get a set of variables that is larger than the set of values, at which point we can derive contradiction in the same way that we derive contradiction for all different. But I never had enough time in any talk to, I mean, I had 20 minutes for the CPIOR talk, and this was at the end of a already quite long Whoops talk. So I have never given a full talk on the details of this. And maybe in hindsight, this would have been more interesting to the Meow people in particular to just go through this in the detail that it deserves. But unfortunately, there's probably neither time nor material to actually do that just now.
So I don't know if you want to go there, but just one, I mean, it would be interesting to know if this is a problem at all or if we should not worry about it. This summing up example seems very nice. I mean, you say if you have a subcycle, then basically you get a positive number that is equal to 0. But what if your subcycle would have passed through vertex 0? Like, do you get any wraparound problems in the because there is when you go from 5 to 0 is like does this affect this summing up argument, or you can somehow elegantly deal with it?
No, it doesn't affect the summing up argument. I'm just maybe we run this on the board.
Because P0 won't be P5 plus 1.
I'm pretty sure this still just derives a contradiction on P0. Because what do we have? We have P0 is equal to 0, P5 is equal to 1, what was the next one? I don't know, P3 is equal to 2, and sorry, I should actually write out what these mean. So x0 equals 5 implies P0 minus P5 is equal to 1. X5 equals 3 implies P5 minus P3 is equal to 1. And X3 equals 0 implies P3 minus P0 is equal to 1. In fact, I think what happens here is x3 equals 0 implies that, yeah, this is a kind of a slight technicality. You're right that I did leave off the encoding, that P3 is equal to n minus 1. Because if you're going back to 0, this must be the last place in the circuit.
Mm-hmm.
This is the only out for the case where this is actually allowed, right? Which is the actual full Hamiltonian circuit, which to be I didn't write in my slides there. So when you add these things up, you're going to get this to P0 equals n, but P0 equals 0. So we're going to get contradiction there as well.
So it's actually just going to work, more or
Yeah,
less.
it does. And you were right to point it out though, because I left off in the encoding, and it is, I promised there in the paper, this extra condition that if it's not actually true that for every xi equals j, that pj is equal to pi plus 1, because we have to get back to the start eventually. So in particular, if j is equal to 0, actually, I think I did put that on the slide, but it was maybe a little bit hidden. Yeah, I did. I very sneakily put, and j is not 0. But yeah, for this case, if j is 0, then we actually want to just say, okay, in this case, I actually don't think we need this constraint at all, but if we want, we can over constrain a little bit and say if xi equals 0, then pi is equal to n minus 1. So if we're going back to 0, we must be in the last position.
Okay. But again, that's just the encoding is going to take care of it, and that you're oblivious to that when you do your summing argument, because the only thing, like if you're passing through vertex 0 somewhere on the way, then you just pick up an extra additive n, and everything else will work. It seems.
This does start to become a problem when we run our strongly connected components counting argument, because we need to start that argument from a particular vertex and then reason about the values that p variables could take if they were x number of steps away from that starting point. And that starting point may not be a fixed value just based on this encoding. And as you'll remember, Jakob, we played around with some ideas of using dominance to arbitrarily start the circuit at any point, because really there's a complete symmetry here. Like this p0 equals 0 is entirely an arbitrary choice. But actually in the CPIR paper in the end, we used extension variables very liberally to effectively define an entirely new set of p variables every time we want to run this argument. And this is partly what gave us the nasty polynomial blowup for the largest examples. But it did mean we didn't have to use dominance or deal with the sort of difficulties there.
Okay.
Just a clarification question. So in practice, these p variables are bit sums in the proof log?
Yes, yeah.
Okay.
All these examples were written before a time that I realized it's really important to not confuse people, to write bits of x rather than just
that part of the bot you cannot see.
Earlier writing, I was just writing x in the PB proof, right? And understanding that we know that we can encode x using a bit sum, but it's really, if you're ever writing arguments like this, it's really worth making this explicit, because it's confused more than one reviewer. Definitely worth doing. Yeah.
Thanks a lot. Any final questions to Matthew? Because I think you've entertained us royally, so we should thank you so much for this. And I think that the examples were a lot of fun.
Hopefully you can trim down a little bit of my waffling in between times there. But I would say I'm relatively happy for most of this to be released as is.
Good. So any final questions? Okay, so let's thank Matthew again. Thank you so much.